All right, so I brought a few slides from previous class, pretty much all of it, I think, just to do review, recap what we were talking about, refresh your minds, and hopefully it makes it easier to follow what we're going to do today. So frames, we talked about frames. We introduced a local frame and a global frame. Local frame or body frame, we said is basically the frame that we attach to the rigid body when we're studying the rigid body. And global frame is the fixed frame. It's always fixed, nothing changes about it, right? But that's just basically the way we define position of a specific point. You can think about that point or particle as a particle or a point on a rigid body, so it's attached to a rigid body. Um, or you can think about it as part of another rigid body. Uh, all that matters is that we wanted to get our notations right. How do we represent the position of a point in a local coordinate frame or body frame or in a global coordinate frame? And it introduced unit vectors. It was just a series of notations that I said we're going to use throughout the course. How to represent a specific point in local or global coordinate frame. Then I started talking about rotation kinematics. Went into details about how can we actually get the new if we have local and global coordinate frame exactly on top of each other at the beginning of the motion. Then we looked at the rotation about the rotational z-axis, and we derived the equations. Uh, the goal was to find the coordinate of the point in global coordinate system based on the coordinates of the point in local coordinate system, like local coordinate frame, right? And since we said the local coordinate frame or body frame is attached to a rigid body, this meant that the final position of the point in global coordinate frame is basically is a multiplication of a rotation matrix, depending on which rotation, the rotation is around which axis, and the position of, or the location or the position of the point in local coordinate frame, either at the end of the rotation or at the beginning, because local coordinate frame is attached to the rigid body that the point is part of. Uh, I just gave you the equations for rotation matrices, and I said pretty much that it boils down to this simple relationship right here, right? That the position in global coordinate frame is the multiplication of rotation matrix, depending on how much we rotate around which axis, by the position in local coordinate frame. Uh, One thing I mentioned that we'll see in one example today, that I said, well, since R is an orthogonal matrix, its inverse and its transpose are the same, which makes our life way much easier when we want to go from the opposite direction. Let's say we know the local coordinates and we want to go and find global coordinates. Instead of finding the inverse of R, which is a 3 by 3 matrix, so to find an inverse of 3 by 3 matrix can be a long process. We can just find the transpose of the matrix. And remember, the transpose of a matrix is basically just switching its rows and columns, right? The first row becomes first column, second row becomes second column, and third row becomes third column. That's pretty much as easy as that to find the transpose of a matrix. So I went over an example. This example, I said, well, let's look at the specific, this slab or block, and we followed point P, well, depending on which step we are, we call it P1, P2, P3, P4. P1 is where it is at the beginning of the motion, right? And we said, well, if there's a specific point P, let's follow that and do a couple of rotations and see if we can find, how can we find the position of the point, the location of the point at the end of rotation. And I said for each step, right, there are like, first step, we said we rotate that 30 degrees about z-axis, then another 30 degrees about x-axis, and then 90 degrees rotation about y-axis. Now, so for each rotation, we go with what we learned. We put global coordinate frame and local coordinate frame on top of each other, matching, and then we make the rotation. And so we can use all the equations that we used before. Right? Uh, another way of thinking about this is that you can continuously move your global and local together, right? Either you can bring back your local to where your global was, or you can take your global to where your local is at the end, and then go for the next step, as if that's the beginning of the motion. Now, the bottom line is, when you have a series of rotations, in this case, 30 degrees around Z, 30 degrees around about X, and another 90 degrees about Y axis. Mathematically speaking, if you actually trace back your steps and see what you did, you will see that at the end, what you all you need to do is that if you know the rotations with respect to global axes, all you need to do is to find those rotation matrices and multiply them. Now, the trick is the multiplication should happen in reverse. So, for instance, if look at this example, right? The first, I multiplied these three rotation matrices, one for 30 degrees about Z-axis, 30 degrees about X-axis, and then 90 degrees about Y-axis. Now, if you go back to the order of rotations, the last rotation is 90 degrees about Z, about Y. The one before is 30 degrees about X, and the one before that, which is the initial rotation, is 30 degrees about Z. Now, if you come back here, the first one goes to the end. So the order is in this way. This is, or let me put it this way. The order of rotation. So you start with the final rotation, multiply that with the rotation before that, rotation matrix. Multiply that by rotation matrix before that, and keep going till you get to the first rotation matrix. And that you can actually follow your, can be seen by tracing your steps right here. So if we start from there right here, this is the first rotation, right? So RZ, RP1. So let me write it. If you trace your steps, let's say you say, I usually write the solutions. Oh, I apparently switched from black to blue for some reason there. All this should be black. So if you think about that, you can think about RP4, right, is equal to, right, RY 90 degrees, RP3. This is the final step that we had right here. Now, RP3, from the previous step, we know that it's RX RP2. So if I plug it back here, this becomes RY40 times R X and 30 degrees RP2. Now RP2, going back to the first step, right there, is RZ30 RP1. So that'll be RY90, this should be 90. RX, let's take this out. This is RX, 30 degrees. And then RP2 is RZ, 30 degrees RP1. So by the end, you will get RP4 is equal to, right, this is rotation matrices, RY90, RX 30, or Z30, this whole thing multiplied by RP1. So again, if you have multiple rotations, all you need to do is to multiply rotation matrices from the last rotation backward. Right? So the last rotation would be the first rotation matrix, the one before that, second rotation matrix, the one before that, up until you get to the first rotation. So remember that order. Order is reverse. So instead of doing it step by step, you can just, by knowing where the P1 is at the beginning of the motion and knowing all the rotations the system has to go through, or the rigid body has to go through, multiply that, find the final R, right? These three by 3 matrices, if you do the multiplication, it gives you a 3 by 3 matrix, R. And that at the end, you just take that R, multiply the position or position of the point at the beginning, and you'll get the position of the point at the end. That's what I want you to, it's a takeaway from this example. All right. Okay, so let's do an example of doing this all together. Question before I move forward, question about the process and how things work. So we're slowly getting into how do we deal with rigid bodies in three-dimensional space. Right? We're getting our notations right. We are defining our frames. Now we're looking at what if the rigid body only rotates. Remember, this is just about rotation. We have this block is not moving, is not translating anywhere. It's just rotating around specific axes. Right? So we're making it step by step. First, let's just talk about rotation. This is what we're talking about. All right, so example. Remember to follow at least my own color code. So we have an arm. Let me bring the if I can find a picture here. There you go. So we have an arm. XYZ defined as global coordinate frame, and just think about it as a simple arm, that a piece of an arm or a link in an arm. Endpoint P is right there. Now, the problem statement is telling you that the endpoint P of the arm first, let me get the pronunciation right. Rotates of the arm let's put it this way. The endpoint P is on the arm, part of the arm, whatever you write it. The arm rotates minus 29 degrees about x-axis, followed by let me move here so I can see you. Followed by 30 degrees about, so minus 92 degrees about x-axis, 30 degrees about z-axis. Okay, z, so let's keep it standard. Z-axis, and again 132 degrees about x-axis. Find the rotation matrix for this, I would say, this rotation and the final position of P, point P. All right, so step by step, let's look at the rotation matrix. We have a rotation, first rotation is minus 92 degrees about x. It's followed by 30 degrees about Z and 132 degrees about X. So three rotations, different rotations. Let's just find the rotation matrix, or I'll call it R total. So it's R, R, R. Now referring back to what I just said, right, we start from the final rotation. That would be the first matrix. You might think that why do I keep emphasizing this? Because it just I've seen a lot of mistakes happen here, so I keep telling you that to remember. So the last rotation is about x-axis 132 degrees. So x 132 degrees. The one before is about z 30 degrees. And then the initial rotation, which is the first one, is about, again, x minus 29 degrees. So let's put them together. Our x 132 degrees. X was 1, 0, 0, 0, 0. 132 degrees, so this becomes cosine 132 degrees. Sine, this is minus sine 132 degrees. Sine 132 degrees. Cosine 132 degrees. First rotation matrix. This is our x 132 degrees. Multiplied by, it's a 3 by 3 matrix. So multiply that by another 3 by 3 matrix, z and 30 degrees. So this is z, this means this is 0, 0, 1, 0, 0. 30 degrees, so this is cosine 30 degrees minus sine 30 degrees, sine 30 degrees, cosine 30 degrees. This would be your R, Z, and 30 degrees. And the final, or better to say, the initial rotation. This is our X, again, minus 29 degrees. 0, 1, 0, 0, 0, 0. Then from there, you'll get a cosine minus 29 degrees minus sine minus 29 degrees, sine 29 degrees, and cosine minus 29 degrees. All right. This becomes R x minus 29 degrees. So we do the multiplication, right? The way you do it, multiply the first two, you get a 3 by 3 matrix, and then multiply the result with the last one. Now you might say that, Masood, I know how to do it in MATLAB or another software. Feel free to do it. I'm not against it. Just remember that your first exam that you have to do it manually, I would say, or if you know how to use your calculator, you can use your calculator. Technically, you're not allowed to use MATLAB. And you will see that it's maybe easy to do it in MATLAB, at least when we have numbers. But later on, when everything is parametric, it's like theta 1 or theta 2 and theta 3, things get a little tricky. We'll use Mathematica for that. But just practice, be comfortable with multiplication of 3 by 3 matrices by hand as well. All right, you can use software to do it. We are going to use software to do it at some point this semester when things get more messy or bigger matrices, and we have to do this continuously. But for now, just get comfortable. Piece of advice: get comfortable with multiplication, matrix multiplication, 3 by 3. Okay, so this is the first one, and then whatever you get here, let's say call this R prime, then this becomes 3 by 3 matrix, and then you multiply that by the next one, and you will get the final matrix. I'll give you a final matrix somewhere here, maybe. Good job by me in terms of space. The components are 0.27 minus 0.44 minus 0.24 minus I have space, why not use it? Minus 0.33 minus 0.15 minus 0.93 0.37 0.89 and minus 0.27. This becomes your final. Let me write it this. So our total becomes this. For the whole rotation, this is going to be the rotation matrix after all these three rotations. Now, this is the first part. We found the rotation matrix. Now, the second part is telling us to find the final position of P. Now, P is part of this arm, right? So as long as I know, remember what we are using. Very straightforward, simple equation. When we say R in global coordinate frame, P is equal to R total, in this case, local coordinate frame, P. Now, the beginning of the motion, we just take them aligned. I assume that they're aligned. Let's say, I used to be able to have arrows there. Okay, I'll use this. Maybe better call it. So let's say these are my also local coordinates at the beginning. I'm just there aligned. Z, X, and Y. It's attached to the arm. It goes through this rotation. Now, in order to find the final position of P, and when they refer to the final position of, when they refer to the final position of P, they are referring to where does it end after these three rotations in terms of global coordinate frame, right? There is no talk of local coordinate frame. Local coordinate frame is something that we attach to the part so we can actually follow the motion. So how do I find that? I need to know this one. I already know this to be able to find this one. Right? Now, what is this? What is this? And looking at this arm, you know, one thing might not be very obvious on this three-dimensional, like in this three-dimensional coordinate system, or at least from the figure, arm is in ZY plane, right? So what are the coordinates, local coordinates, or RP in local coordinate system?
We know that x is equal to 0.
X is equal to 0, exactly. So let's put this B right there. So I'll write it here, so we have it right where we want it. You know, or I can't do it here. You know what? I'll just bring that again. Nobody's stopping us from bringing the picture again. Why are we? Instead of going back and forth. So, R P in B, right, the components. We know that, as Pamela said, X is 0. So, X, Y. So components, I want to write them. Let's write it in vertical. I do have a space here. 0. What is Y?
I guess we could assume like a unit circle, so it'd be like the cosine of 75.
Exactly. So y would be cosine 75 degrees, and as a result, z would be sine 75 degrees. Now you can see it here if, let's do it this way. See if I can. Right there. Oh, God, that's not. There we go. This is very true. But if this angle is 75 degrees, this becomes cosine 75 degrees, and this becomes uh, z value becomes, this is sine 75 degrees. In case you're not following, just make sure everyone is following. So cosine 75 degrees, sine 75 degrees on y and z axis. That's pretty much it. Once you know r, position of p in local coordinate frame, right, the b frame that we call there, then we can actually find the position of p in global coordinate frame at the end of the motion. So let me call it p1 and call this p1 position. Just want to make the notations right. Position of point p at the beginning of the motion. Once we got that, then we have 3 rotations. So let's say P2, P3, P4. This would be position of point P in at the final, in the final. Position of point P at end, the end of the motion. Well, you do have this main matrix R2 already. You calculated that, and this it's a 3 by 3 matrix. This is a 3 by 3 matrix, and now you have the coordinates. You can just put the coordinates right here. 0 cosine 75 degrees, sine 75 degrees. So another multiplication. This time you multiply a 3 by 3 matrix by a 3 by 1 vector. Well, the result should be a 3 by 1 vector.
Dr. Masumi,
Yes.
for the when you're multiplying the three matrices, I got a different answer for the top left number.
You did. Hopefully, maybe I need to fix somewhere in my note.
I got 0.87.
It is actually 0.87. I have a vision problem apparently. Looking at my notes. Thank you for pointing that out, Michael. It is 0.87.
Okay, thank you.
Of course, I'm that guy who cannot write his own handwriting, I guess. Yeah, it is 0.87. Should be. All right. So 3 by 3, 3 by 1, matrix by vector should give you a vector. So that gives you R. I don't even need to write it in a separate place. I'll write it here. IP RP4 in global coordinate frame. That'll give you minus 0.35, minus 0.94, and then minus 0.031. That would be the position at the end. That's what we were looking for. Right. Again, pretty straightforward procedure. Very, I would say, easy. As long as you just understand what is going on, the math is very straightforward. A bunch of rotations, you know where you are at the beginning, you want to know where you are at the end. Following through these rotations. Let's see, I have a couple more examples. Why not going through them? So the next one is a general form, I believe, or let's Yeah, why not? Let's go over this example. It's the pretty much just the general form of assuming that we have three rotations. Three rotation. The reason we keep talking about three rotations is because a lot of motions, a lot of rotations, or even generally translation and rotation motion in general, which includes both translation and rotation. The rotation part can pretty much be defined using three rotations maximum. Right? Sometimes two, sometimes just one. Maximum using three rotations, you can get to where you want to be from where you are. Right? Again, think about in general picture when you are dealing with the robot arm, you want to design the path, you want to go from one place to another. With three rotations, typically three rotations is good enough. That's why there are, if you see in different references, look at different references, you see they provide you with typical results for typical rotations like X, Y, Z, X, Z, Y, Y, X, Z, different rotations, possible rotations. Just a general formula, and you can just pretty much plug those in and plug the angles that you have and use those instead of doing the multiplication from the beginning. So for sake of completeness, let's look at one of them. Find the rotation matrix after a rotation or Z alpha followed by or Y beta, and then followed by or X gamma. So it's just a series of multiplications. You already know what R Z alpha is in the form of. Now, one thing I want to mention, both I do it and in the textbook, you'll see that the textbook starts doing it, and later on you will see why the matrices become very huge. So it's very energy consuming, I would say, writing sine, cosine continuously. So you will see a lot this type of abbreviation that we use C for cosine and we use S for sine when we are writing these matrices. So if you follow that note, this becomes cosine alpha minus sine alpha is 0. Then it becomes sine alpha cosine alpha C, basically C alpha 0 and then 0, 0, 1. It makes the writing much easier instead of keep writing sine, cosine. Right? This is followed by R, Y, and beta. Right? We also know that one already. So this is cosine beta 0. This is 0, 1, 0. And this is also 0. This becomes sine beta. This is minus sine beta. And this is cosine beta. Let me double check if I wrote correctly. Yes, that's it. Was. And then you have R, X, and gamma. It's X, so this is 1, 0, 0, 0, 0. Then you have cosine alpha. You can write it as C. Cosine alpha, cosine gamma, it's gamma, minus sine gamma, and then sine gamma and cosine. A tendency to go for cosine gamma instead of C. So the total rotation, well, you can get that by just multiplication. Total rotation will give you, well, we start from the end, right? So R total, if I refer to it as R total, we start from the end, R X and gamma multiplied by R Y is the second one, and beta beta amount around y-axis, and rotation alpha amount around z-axis. Let's just write this z as without, so I follow my own notation correctly. Right. So let's do the multiplication. If I do the first multiplication, just we have it in our notes, and later on you want to check how the multiplication works. Again, 3 by 3 matrix multiplication. I'm multiplying Rx gamma and Ry beta. Right? So first row multiplied by first column, this gives me cosine beta. First row with second column, right? So that becomes 0 cosine multiply first row by second column 0 0 0, pretty much 0. First row by third column becomes sine beta. Let me spread them a little bit so I have room to 0 sine beta. Second row of Rx gamma multiplied by the first row of Ry beta, 0 0 sine beta, basically sine beta, sine gamma, sine beta, sine gamma. Double check. Sine beta, sine gamma, minus goes away. Second row with second column, second row of the first matrix by second column of the second matrix, 0 cosine gamma 0. So this becomes cosine gamma. And then this one becomes 0 0 sine minus sine gamma cosine beta. And finally, this is third row with the first column, 0 0 minus sine beta sine cosine gamma cosine gamma. Third row with the second column, 0 sine gamma. Basically, this becomes sine gamma. And third row with third column, 0 0 cosine gamma cosine beta. And then you multiply this by R, Z, and alpha. If you do that one, I'll just write it from my notes before you guys go to sleep, listening to me just multiplying these random elements. So just remember, this is a 3 by 3 matrix. This is also a 3 by 3 matrix. So we'll just multiply those. This gives you at the end cosine alpha cosine beta. I have to move things all down. Probably seems like I have a space management problem. There you go. This is R total. The first element is cosine alpha cosine beta. The second element becomes minus sine alpha cosine beta, and third one would be sine beta. Second row, you do the multiplication, double check your work and make sure that you actually get the same thing. Cosine alpha, sine beta, sine alpha, cosine, sine gamma, cosine alpha, plus, let me put it right in front of me, plus cosine gamma, sine alpha. Second element would be minus sine beta, we got it beta. Don't want to write something wrong and then later on you get a different number, and then sine gamma, although you already know you have to trust yourself, but just to make sure that minus sine gamma cosine beta, then minus sine beta cosine gamma cosine alpha plus sine alpha sine gamma, and then sine gamma cosine sine gamma cosine alpha, and eventually cosine gamma cosine beta. Last check, especially second row, sine gamma cosine alpha plus cosine gamma sine alpha minus sine beta sine gamma sine alpha plus cosine gamma cosine alpha minus sine gamma cosine beta, sine beta cosine gamma cosine alpha plus sine alpha sine gamma sine gamma cosine. Okay, believe it's correct. So the bottom line is these things can get very messy very fast. Right? The matrices start growing. You will see later on, especially when we do we follow the process for 4x4 matrices. Just get comfortable with doing the multiplication. Right? At least 3x3 matrices by 3x3 matrices. Like this is the I guess max we're gonna do by hand, and then later on things get a little easier. At least I think so. When you're dealing with when you're using software. All right. So again, remember, I'm saying this again. When you do a series of rotations, start from the end, come back to the beginning when you want to find the rotation matrix. Let's do one more example with numbers. I want to use or take advantage of the fact that we introduced, if you remember in a note, I said the transpose of a rotation matrix is equal to its inverse. Right? So let's see how does that help us. A very simple case would be when we know the local coordinates of a point after it's moved. Right? Say it's moved at the end of the motion. We know we put the local coordinate on the system, and we are told that if this is the local coordinate, this is the position of this point of the rigid body at the end of this rotation. Right? And now we're asked to find what was the initial position. And remember, initial position can be they're the same in local and global coordinate frame, because at the beginning both frames are sitting on top of each other. So, example. This goes as find the local coordinates of point P after it's moved, better to say it's rotated. Well, I'll refer to it later on. After it's moved to RP2G, let's move to RP2G as, what is that? The numbers are 4, 3, and 2 transpose. So it's basically a vertical. The vector in this direction is 3 by 1. I write it as 1 by 3 in transpose. It takes less space, but it basically is 3 by 1. Through 60 degrees rotation about the z-axis. So we know where it is at the end. We want to know where it was at the beginning. It's asking to find the local coordinates of point P at the beginning, but again, remember, it depends on how you define your coordinate system. So pretty much you can think about it as RG in P2 is equal to rotation matrix, in this case rotation about Z for 60 degrees times R P2 in body frame. local coordinate frame. Plugging in the values, and you have 4, 3, 2 multiplied by, well, the rotation about z-axis 60 degrees. This would be 0, 0, 1, 0, 0. This is cosine 60 degrees. This is minus sine 60 degrees, sine 60 degrees, and cosine 60 degrees. And I multiply that with the coordinate. Let's call it x2, y2, z2, whatever it is. That's a very simple example of how this is your R rotation matrix, and it's 3 by 3. This is 3 by 1. This is 3 by 1. So we want to find this one. The way we find this, we just take this R matrix to the other side, an inverse of that, or you can think about it multiplying both sides by an inverse. This is a matrix equation. So your unknown is on the right side. To find that unknown, you multiply both sides with R inverse. You can think about it that way. Or simply, you can just take R from this side and take it from the right side and take it to the left-hand side. It becomes inverse, comes up. Multiply that by 3, 4, 3, 2 matrix vector, and you get your x2, y2, z2. Right? So let's write it this way. Your x2, y2, z2 becomes this matrix, cosine 60 minus sine 60, 0, sine 60 degrees, cosine 60, 0, and 0, 0, 1, right? Inverse 4, 3, 2. Now, the note we mentioned, inverse and transpose are the same. Instead of going through the whole process of finding the inverse of a 3 by 3 matrix, since it's an orthogonal matrix, we know that this is R, this is R. So we know that R inverse is equal to R transpose. So all you need to do is just to find a transpose. This becomes, let me continue this line. x2, y2, z2 is equal to, what is the transpose of that? So we have the first row, cosine 60 minus sine 60, 0. It said first row becomes the first column. So cosine 60 minus sine 60, 0. Second row becomes the second column. This becomes sine 60, cosine 60, 0. Third row becomes this third column, 0, 0, 1. Multiply that by 4, 3, 2. This is R inverse is equal to R transpose. It's basically R transpose. And then that's easy. Right? Just again, the matrix multiplication. Multiply this 3 by 3 matrix by 3 by 1 vector. You will get a 3 by 1 vector. Obviously, the elements of the result are going to be corresponding values for x2, y2, and z2. Right? If you do that multiplication, you eventually get, I'll leave it to you. Again, if I keep writing numbers, which already probably have to sleep. 4.6 minus 1.96 and 2. So pretty much you get x2 as 4.6, y2 is 1.96, and z2, this is not, I am even getting confused with my z and my 2. This is 2. z2 is 2. So we found the local coordinates. These were the local coordinates. I remember x2, y2, z2 are the same as x1, y1, z1. Right? Going back to where we were proving this, or we were deriving the equations, right? X2, look at the pink, I guess, color. X2 is equal to X1. So X, Y, Z coordinate, local coordinates in one motion, in one rotation, they don't change because the local coordinate frame is attached to the rigid body that we are looking at a specific point of it. So before and after motion, X, just one rotation I'm talking about. Coordinates in local coordinate frames are the same. So when you find, going back there, X2, Y2, Z2 is pretty much just the same as X1, Y1, Z1. Right? It's just the same. You can, even from the beginning, you can just put X1, Y1, Z1. All right. Question about this. Hopefully now everybody's comfortable with the whole process about rotation. Right? That's pretty much all you need to know about rotation. There's nothing else I expect you to know. Now, if you look at the textbook, there are probably more stuff going on there. I did not really, I'm not going to talk about all of it because we want to go faster and get to the way I call it, more exciting stuff. Right? I do solve as many examples as I can, but we're just going to skip the parts that are not going to help the final goal for this course, that we want to be able to analyze the kinematics of a robot arm and also be able to design path for specific motions. One last thing about something that you will hear when it comes to rotations is about roll, pitch, and yaw angles. This is something you will see in aerospace. You will see in if you talk to naval engineers, like when the people driving, designing ships, and I would say submarines, designing or working in aerospace area. They talk about roll, pitch, and yaw angles. Pretty easy. It's just a terminology. Right? Roll, we say roll is when we have rotation on x-axis is called roll. When we have rotation on y-axis is called pitch, and when we have rotation about z-axis is called yaw. And that's it. Just want to mention that here. So roll, pitch, yaw. All right. I also have a picture here just to have it in your notes. Again, not a big deal, but just if you hear it somewhere. Right. So I'll just briefly say roll, or let's say this way, rotation about x-axis is roll, rotation about y-axis is pitch, and then eventually a rotation about z-axis is yaw. That's pretty much it. I don't really have that much more to add. Few things again. We only talk about local global coordinate frame rotation about global coordinate frames axes. Now, if you look at your textbook again, there are separate sections about rotation about local coordinate axes. Now, I don't talk about them because it makes things much more confusing, which is kind of unnecessary for this course. If you have advanced dynamics, maybe that's where it comes more into play. But just knowing the rotations about global axes, global coordinate frames axes, is good enough for us to be able to analyze and look at motions of robot arm. Just learn this. I promise you that it's good enough. It's more than enough. It is enough, not more than enough. It's enough to be able to look at kinematics of robot arms. And we'll take it from there. So as a result, since the book talks about rotation about local coordinates, coordinate like local axes, local frame axes, you will see roll, pitch, and yaw defining in that way as well. Right? Rotation about x, y, z, but in local coordinate frame. And last thing that you'll see in textbook that is actually a very important concept, but again, doesn't help what we cover in this course. If you have advanced dynamics, you take that course, that's where exactly that it comes into play, and it actually has a more important role in analyzing motions in three-dimensional space. Here in this course, again, we really don't need it. And that's the concept of Euler's angles. Euler's angles you see in your textbook. I can take a look and tell you where to look at if you want to know more about Euler's angles. Give me a minute. In your textbook, I believe this is, you'll see this section 2.6. A little bit of rotation. You need to know rotation about local coordinate frames and use that to get a better sense of Euler's angles. But if for any reason you need to know those for any other research you're doing, or you feel like it's needed for something else that you're studying, it's in section 2.6 in your textbook. Okay. So two things I'm not going to talk. So we have more time to move forward, cover more examples, and look at more interesting, I would say, things that we want to talk about. Euler's angles and rotations about local coordinate frames. And I think that one in your textbook probably you can also find in couple parts, but the starting point is section 2.4. So local coordinates. Section 2.4 is where it starts talking about it, and then you see talking about successive rotations that we talked about, roll, pitch, and yaw defined in local coordinates. So it's, I would say, 2.7, 2.8. These are talking about local coordinates, how to go from same concepts, but we talked about for global coordinate system, just for local coordinates. Again, this is robotics introduction, and I prefer to stay focused on the things that we can use later on for multiple purpose, from looking into kinematics of a robot arm and also looking at how to design path. All right, but just so you know, if you look at your textbook, you'll see multiple sections. Don't worry about it, right? We did not talk about it, and that was the purpose. All right, so let's see, how much time do I have? I think I have some time. Let's okay. So let's, just for the purpose